Hello, welcome back to more of the final exam review. We're going to start with question number 5 today. It says, suppose X is a normal random variable with a mean of 100. Use the given normal distribution to answer the following. Do not use any of our Desmos. You won't be able to because we don't know the standard deviation. So everything about this curve is going to have to be intuitive about what we know about the empirical rule. So I am just going to draw some things on here. I know that my mean is 100. So it says find the probability that X is greater than 83. Well, if I know that the probability that X is less than 83 is 0.04457, I know that using the complement, I can find the space that's greater than. So this is going to be equal to 1 minus the probability that X is less than 83, which is 1 minus 0.04457. And that should be equal to 0.95543. If I subtracted correctly. Find the probability that X is greater than 117. Okay. So intuitively also, I can see that 83 to 100, there are 17 spaces here. And so whatever another 17 spaces this way would be 117. I know that those probabilities are the same. I don't know what an exact standard deviation probability is, but I know that these spaces equal this probability. So it says the probability that X is greater than 117 is this space right here, which matches the space that's less than 83. So it should also be the same probability. Next says, find the probability that X is between 83 and 117. So that is between the two spaces that we already know. So that means it's going to be 1 subtracting 2 of the 0.04457s. And we can do that on Desmos. Here, I'm going to do that down here at the bottom. So 1 minus 2 times 0.04457. And so that space should be 0.9106. And then the last piece says, find the probability that X is between 83 and 100. So that would be 100 marks 0.5. I'm going to just go back and share my screen so you can see. So this is the answer to the last question. Part D says between 83 and 100. So that's this space right here. And I know that everything less than 100 is 0.5 because that's where our center is. So I can take 0.5 and subtract away the 0.04457, and we get 0.45543. So this is all kind of intuitively knowing the truth about the normal curve and the percentages and how they're related using complements. We used a lot of complements. Okay, question 6 and 7 relate to finding the critical Z values. And this is important because we use critical Z values in confidence intervals, hypothesis testing. So it says, suppose Z is a standard normal random variable. Show all work here. So we're going to try to include some graphs so we can get a picture of what's going on. It says, find the probability that Z is between a negative 2.13 and negative 0.35. So they're both negative. So a negative 0.35 is over here to a negative 2.13. So we are going to look here. So because Z is normally distributed with a mean of 0 and a standard deviation of 1, we can use our curve in Desmos. So if we go to our screen, our Desmos screen, I've got my inverse up here and I've got my normal. So we want to find probability. So we're going to use the normal distribution. And I want to find it between a negative 2.13 up to a negative 0.35. And I can just click on my Zoom fit and I can see that this is exactly what I had drawn on my paper. So for number 6, part A, the probability is 0.3466 rounded to 4 decimal places. So let's stay right here. B says find the area to the left of Z equals 2.34. So we want to find the area. So it's a probability that Z is less than 2.34. And 2.34 is positive. So that means we're going to have an infinity over here on the left. And then 2.34 on the right. And so it's quite a big space. It's a very large probability. So letter number 6B is equal to 0.9904 when we round to 4 decimal places. Okay, letter C says to the area to the right of Z is 0.07. Find Z. Okay, go back to the paper for a moment. Here are my answers for A and B. So on this one, we know the area to the right of Z is 0.07. So it's something over here. And we want to find the Z of that. So we're looking for the Z of 0.07. But we have to remember in Desmos, Desmos only lets you insert in the inverse 1 minus 0.07, the left-hand area. So in Desmos, we have to use 1 minus 0.07 for it to calculate. So let's go ahead and go back to Desmos to show you how that's done. So that's where we're going to use the inverse up here. So it's normal 0 and 1, and we want 1 minus, and ours is 0.03 that we're, or 0.07. So that Z-score would be 1.4758 when we round to 4 decimal places. And that's right where my mouse is here. This is my answer right here. Okay. Letter D says find the Z. So we're finding Z again, such that the area to the left of it is 0.23. So let's go back and look at a picture again. So we're looking for the area to the left is 0.23. So it's somewhere maybe right around in here. And so this is going to be a negative Z. And the cool thing is we have the left area, and that's what Desmos likes. So we're finding a Z such that the area to the right is 1 minus 0.23. But that's okay, because this is what we're going to enter into Desmos. And let's find that critical Z. We know it's going to be a negative value because it's on the left. Let's go back there. And so we can delete the 1 minus and put in 2, 3. And the Z-score is a negative 0.7388. I'm going to share my paper so you can see the answers to verify these here. For sale. Okay. Let's move on to question 7. Question 7 says, find the following critical values. So similar to what we did before, but it's saying find a critical value. It's a negative z for a left tail test with alpha at 0.0015. So a left tail means we're going to use the alpha just as it is, and it's a negative z value. And we can look and see, this is not on 0.015, is not on our table here. But we know that it's somewhere between 0.01 and 0.015. So it's going to be somewhere in here in a negative version. So negative 2.326 to negative 2.5. But again, because it's the negative, it's going to be some z over here. And left tail means it's a negative z. So it's the negative z of 0.015. And so we're going to go back to our Desmos here, and we can put in 0.15. And it's a z that's negative 2.17. Just like what we had thought. Somewhere between the two that the other direction a little bit, negative 2.17. Okay, now part B says for, let's go back to my paper. Now we're going to find a T alpha, a critical T for a right tail test with alpha at 0.02, where n is equal to 7. So we have to remember when we're using the critical T values, we're using degrees of freedom, which is equal to n minus 1 or 6 in this case. So we want to find degrees of freedom is 6, and alpha is, it's a right tail test, so we're using alpha. We don't have to divide by 2 at 0.02. And that is in our table, which is really cool because 0.02 is in our table. We can go to degrees of freedom of 6 and over to 0.02. And the answer is 2.612. Okay. So let's look at question number 8. Question number 8 is more of a chapter 1.6 question. The 4 members of Skylab had their lymphocyte count per cubic millimeter measured one day before liftoff and measured again on their return to Earth. Give the explanatory variable or treatment. Okay, so their explanatory variable treatment is going up into space. Because the pressure up there is going to be different. So that's what they're saying is maybe changing this lymphocyte count. So the response variable is what are we measuring? We're measuring the lymphocyte count. And what are the experimental units? They're the count per cubic millimeter. Oh, I'm sorry. The experimental units are the people, the 4 members of the Skylab, the people that we're testing this on. So 4 members of Skylab. And what type of design is this? There is a before and after. They weren't randomly chosen, so it could be kind of considered designed or observational. Even though they didn't randomly choose them, this would be probably considered more of a designed experiment because they are doing a test before and after. And there's no way you could ever do a randomly chosen group of people to go up to space because they have to be trained for so long before. Okay. The last question in this video is going to be question number 9, and then we're going to move on. So question number 9 says, the distribution for a population of test scores is displayed below and in the top left corner. So this is our population distribution. It's definitely a skewed left. Each of the other 5 graphs, A through E, represent possible sampling distributions of sample means for 500 random samples drawn from the population with sample sizes of 1, 2, 4, 6, and 8. Match each graph with its respective sampling distribution. Place the number for the sample size by the letter. Okay, so the population distribution can be skewed, but when we start taking samples, the bigger the sample size, the more the sample is going to be normally distributed because the samples will be similar to each other. Okay, so the ones that is still very skewed left, which would be letter D, is going to be the sample size of 1, and then this other one is going to be sample size of 2, and then it's getting less and less. Oh, wait. Let's see here. It's going down. So this one will be 2, and this one will be 4. It's becoming more and more normally distributed. So this would be the sample size of 6, and this would be the sample size of 8. So A and C are kind of interchangeable, but you can see as the smaller sample size is definitely going to be the ones that are still skewed left, like the population. When it becomes very normal, that's when we get to the bigger sample size. And so that concludes this video. Catch me back for some more review videos.